So here's something worth thinking about as you settle in tonight. Everything around you, and I mean everything, the pillow under your head, the air filling your lungs right now, the glass of water on your nightstand if you've got one there, all of it is chemistry. Every single object you have ever touched, every breath, every sip, every smell that's ever drifted past you, it's all atoms doing their quiet, ancient dance. And the story of how we figured that out, how we went from having absolutely no idea what anything was made of, to understanding matter at the level of individual electrons, that story is one of the great human adventures. It stretches back thousands of years, and it's full of wrong turns and lucky accidents and people who were brilliant and people who were stubborn, and honestly, quite a few people who were both at the same time. Let's start where it makes sense to start. Not in a laboratory, because there weren't any laboratories. Not with a periodic table, because nobody had dreamed of one yet. Let's start with fire. Fire might be the oldest chemistry experiment. Think about what happens when you burn a piece of wood. You start with something solid, something brown and hard and heavy, and you add a flame, and it transforms. It gives off heat and light. It crackles. Smoke rises. And when it's done, what's left? A small pile of ash that weighs almost nothing compared to the log you started with. Where did the rest of it go? That question, that simple, obvious, staring you in the face question, would take humanity thousands of years to properly answer. But the fact that people notice the question at all, that's where chemistry begins. The earliest people who worked with chemical transformations didn't call it chemistry, of course. They were potters and metalworkers and dyers and brewers. They were practical people solving practical problems. Somewhere around 9,000 or 10,000 years ago, people in the ancient Near East figured out that if you took certain kinds of clay and heated them in a fire hot enough, the clay changed. It went from soft and squishy to hard and permanent. That's a chemical transformation. The heat was breaking apart the water molecules trapped inside the clay's mineral structure and causing new bonds to form, locking the silicate minerals into a rigid framework. They didn't know any of that, obviously. They just knew that fire plus mud equaled something useful, and that was enough. Then came copper. This is a big deal, and it's worth slowing down for. Sometime around 5000 BCE, probably in several places somewhat independently, people discovered that certain greenish rocks, when heated in a very hot fire, would weep out a shiny reddish liquid that hardened into metal. That's smelting. What was happening, in terms we'd use today, is that the copper ore, likely malachite, which is a copper carbonate mineral, was being reduced. The carbon from the charcoal fire was ripping the oxygen atoms away from the copper, releasing carbon dioxide gas and leaving behind pure metallic copper. It's a redox reaction, one of the most fundamental types of chemical reaction there is, and ancient metalworkers were doing it millennia before anyone had a word for oxidation or reduction. And here's what's really lovely about this. They didn't need to understand it to use it. They just needed to notice that it worked, and then do it again, and then teach their children to do it. Chemistry, in its earliest form, was a craft tradition. Knowledge passed hand to hand, generation to generation, through apprenticeship and observation and trial and error. A lot of error. The jump from copper to bronze is another beautiful piece of accidental chemistry. Bronze is an alloy, a mixture of copper and tin. Somebody, somewhere around 3000 BCE, maybe in what's now Turkey or Iran, discovered that if you melted copper and tin together, the resulting metal was harder and more durable than either one alone. That's because the tin atoms, which are a slightly different size than copper atoms, disrupt the neat crystal lattice of pure copper. They make it harder for the layers of atoms to slide past each other. It's like putting a few large marbles into a tray of small marbles. Everything locks up a bit more. That simple metallurgical insight, mixing metals to make something stronger, was so important that we named an entire age of human civilization after it. The Bronze Age. That's chemistry shaping the course of history. But let's leave the metalworkers for a moment and travel to ancient Greece, because something different was happening there, something more abstract. The Greeks, particularly the philosophers of the 5th and 4th centuries BCE, started asking a question that craftspeople hadn't really bothered with. Not, how do I make this work? But what is stuff actually made of at the deepest level? There's a man named Leucippus and his student Democritus working around 450 to 400 BCE in the Greek world. And Democritus had this thought experiment. He said, imagine you take a piece of cheese, you cut it in half, then you cut one of those halves in half, then again and again. Can you keep cutting forever, getting smaller and smaller pieces of cheese into infinity? Or do you eventually reach some tiny fundamental piece that can't be cut any further? Democritus believed you'd reach that limit. He called those ultimate uncuttable pieces atomos, atoms, from the Greek for not cuttable. Now, Democritus didn't have a microscope. He didn't have any experimental evidence for this. It was pure philosophical reasoning, a thought experiment. And honestly, a lot of his specific ideas about atoms were wrong. He thought they came in different shapes, that some were smooth and some were rough, and some had little hooks on them, and that those shapes explained why things felt and behaved differently. But the core insight, that matter is not infinitely divisible, that there are fundamental building blocks, that idea turned out to be profoundly, spectacularly correct. It just took about 2,000 years for anyone to prove it. And here's the thing. Democritus didn't win the argument in his own time. Not even close. The philosopher who dominated Greek thinking about matter was Aristotle, and Aristotle thought Democritus was wrong. Aristotle's view, which became the standard model for an almost unbelievably long time, was that all matter was made of 4 elements: earth, water, air, and fire. These weren't elements in the way we use the word today. They were more like qualities or principles. Earth was cold and dry. Water was cold and wet. Air was hot and wet. Fire was hot and dry. And Aristotle believed that by changing the balance of these qualities, you could transform one substance into another. Change the proportions, change the material. Now, you might be thinking, that sounds pretty wrong. And it is. But try to see it from Aristotle's perspective. Look at what happens when you heat water. It turns into steam, which rises like air. So maybe water is becoming air? Look at what happens when you burn wood. It gives off flame, which is fire, and smoke, which rises like air, and it leaves behind ash, which is earthy. So maybe wood is a combination of fire and air and earth? The 4-element theory actually does a surprisingly decent job of organizing everyday observations, as long as you don't push too hard on the details. And for centuries, nobody pushed too hard. Aristotle's influence is hard to overstate. His ideas about matter, along with the rest of his philosophy, became deeply embedded in European and Islamic intellectual traditions. They were taught in universities. They were woven into theology. Challenging Aristotle wasn't just an academic disagreement, it was borderline heresy in some times and places. And that meant the four-element theory hung around for a very, very long time. But while the philosophers were debating abstract principles, practical chemistry kept marching forward. In Egypt, and later across the Islamic world, a tradition emerged that we now call alchemy. The word itself probably comes from the Arabic alchemia, which might trace back to the ancient Egyptian name for Egypt, Kemet, meaning the Black Land, a reference to the dark, fertile soil of the Nile Valley. So alchemy might literally mean something like the Egyptian art. Alchemists get a bad reputation, and some of it is deserved. The popular image is of a wild-eyed mystic trying to turn lead into gold. And yes, that was definitely part of the program. The idea of transmutation, changing one substance into another, was central to alchemy. And it made a kind of sense within the Aristotelian framework. If all matter is just different combinations of the same four elements, then in principle, you should be able to rearrange those elements to turn a base metal into a noble one. You just need to find the right process, the right catalyst, the right secret ingredient. Alchemists called this hypothetical substance the philosopher's stone, and the search for it consumed lifetimes. But here's what's really important, and what often gets lost in the caricature. Alchemists were experimentalists. They built furnaces and distillation apparatus. They heated things and cooled things and mixed things and observed what happened. They kept records, sometimes in deliberately obscure language because they wanted to protect their secrets, but they kept records. And in the process of chasing their impossible dream of transmutation, they discovered an enormous amount of real, practical chemistry. Take Jabir ibn Hayyan, who worked in the Islamic world around the 8th century CE. There's some scholarly debate about which works attributed to him were really his and which were written by later followers using his name, but the body of work associated with Jabir is remarkable. The Jabirian corpus describes the preparation of dozens of chemical substances. It describes distillation techniques, the use of chemical baths, methods for producing what we'd now call hydrochloric acid and nitric acid, and even something close to aqua regia, the mixture of acids that can dissolve gold. Jabir, or the tradition bearing his name, also introduced a systematic approach to classifying substances and described processes like crystallization and sublimation with real precision. And Jabir wasn't alone. Across the Islamic world during what's sometimes called the Islamic Golden Age, roughly the 8th through the 14th centuries, scholars were doing extraordinary chemical work. Al-Razi, known in the West as Rhazes, working around 900 CE in Persia, wrote a book called The Secret of Secrets that classified substances into categories that start to look surprisingly modern. Spirits, which were volatile substances that could be vaporized, metals, stones, salts, and other categories. He described specific gravities and chemical tests for identifying substances. He was moving, slowly and imperfectly, but genuinely, towards something that resembles systematic chemistry. These scholars also refined and improved laboratory equipment. The alembic, which is a type of distillation apparatus with a distinctive rounded flask and a long downward-pointing spout for collecting condensed vapors, became a standard tool during this period. If you've ever seen an old-fashioned whiskey still, you're looking at a descendant of the alembic. Distillation itself, the art of separating substances by their different boiling points, is one of the most important techniques in all of chemistry, and it was alchemists who perfected it. So when you think about alchemy, don't just think about the gold-making nonsense. Think about the centuries of patient, hands-on experimental work that built the toolkit chemistry would eventually need. Think about the furnaces and the flasks and the careful observations, all happening in the service of a theory that was fundamentally wrong, but that drove people to do real, important work anyway. There's something almost poignant about that, isn't there? All those brilliant minds chasing an impossible goal, and yet the things they discovered along the way turned out to be far more valuable than any philosopher's stone could ever have been. By the time alchemy crossed back into medieval Europe, filtering through translations from Arabic into Latin, it carried with it this rich legacy of practical knowledge. European alchemists inherited the equipment, the techniques, and the ambition, and some of them began to push the tradition in new directions. One of the most interesting figures in this transitional period is a Swiss physician who called himself Paracelsus, though his real name was the wonderfully unwieldy Theophrastus von Hohenheim. He was born in 1493, and he was, by all accounts, an absolutely impossible person. Brilliant, arrogant, combative, he publicly burned the books of Galen and Avicenna, the reigning medical authorities, to signal that he was done with tradition. He wandered across Europe, picking fights with the medical establishment everywhere he went, getting run out of one city after another. But Paracelsus had an idea that would prove enormously influential. He believed that the purpose of alchemy wasn't to make gold, it was to make medicines. He argued that diseases were caused by specific chemical imbalances in the body, and that they should be treated with specific chemical remedies. This was radical. The prevailing medical theory was still based on the ancient Greek idea of four humors, and treatment mostly involved trying to rebalance those humors through bloodletting and purging and other fairly miserable procedures. Paracelsus said no, the body is a chemical system, and when it goes wrong, you fix it with chemistry. He introduced mineral and chemical remedies, compounds of mercury and sulfur and antimony, into medical practice. Some of them were genuinely useful. Some of them were genuinely toxic. But the principle that chemistry and medicine are deeply connected, that the body is something you can understand and treat through chemical knowledge, that principle was genuinely revolutionary. It planted a seed that would take a couple of centuries to fully sprout, but once it did, it changed everything about how we think about the relationship between chemistry and the living world. And Paracelsus left behind another idea that's worth sitting with for a moment. He's often credited with the phrase, "The dose makes the poison," which, even if the exact wording is debated, captures something he absolutely believed. That any substance, even water, even air, could be harmful in the wrong amount, and that substances we think of as poisons could be healing in the right amount. That's a deeply chemical insight. It says that the effect of a substance isn't just about what it is, it's about how much of it there is and how it interacts with the system it enters. That's a principle that modern pharmacology is still built on every single day. Every time a doctor calibrates a dosage, every time a pharmaceutical company runs a clinical trial to find the therapeutic window of a new drug, they're working within a framework that Paracelsus, this cantankerous, wandering, book-burning Swiss physician, helped to establish 500 years ago. But let's zoom out a little, because the 16th and 17th centuries are this fascinating period where alchemy and what we'd recognize as chemistry are kind of coexisting, overlapping, slowly separating from each other like oil and water in a jar that someone stopped shaking. there are still plenty of people searching for the philosopher's stone. Still plenty of people trying to turn lead into gold. But alongside them, there's a growing number of people who are starting to ask different questions. Not, how do I make gold? But, what is this substance actually made of? How does it behave? Why does it react this way and not that way? One of the key figures in this transition is a Flemish physician named John Baptist van Helmont, working in the early 1600s. Van Helmont is a fascinating character because he's got one foot in each world. He still uses some alchemical language, still believes in some alchemical ideas, but he's also doing something that looks remarkably like modern experimental science. He's measuring things, he's weighing things, he's keeping careful records, and he makes a discovery that seems simple but turns out to be profound. He realizes that there are different kinds of air. See, up until this point, most people thought of air as just air. One thing, an element, in the old Aristotelian sense. Van Helmont notices that when you burn charcoal, or when you ferment wine, a gas is produced that's different from regular air. It's heavier. It extinguishes flames. You can't breathe it. He calls it gas sylvester, wild gas, and what he's actually identified is carbon dioxide, though he doesn't have that name for it yet. In fact, the word gas itself, that's Van Helmont's invention. He coined it, probably from the Greek word chaos, and it stuck. Every time you say the word gas, you're using a term invented by a 17th century Flemish physician who was curious about why burning charcoal produced something invisible that could snuff out a candle. Now, here's the thing about Van Helmont's discovery. It doesn't seem like much on its own. Okay, there are different kinds of air, so what? But it opens a door. Once you realize that the invisible stuff around us isn't just one uniform substance, once you realize there are different gases with different properties, you've cracked open a whole new territory for investigation. And over the next century and a half, that territory is going to yield some of the most important discoveries in the history of chemistry. But before we get there, we need to talk about Robert Boyle, because Boyle is one of those figures who really does stand at the hinge point between the old world and the new. Born in 1627, he was the 14th child of the Earl of Cork, one of the richest men in Britain. So he had the resources to do pretty much whatever he wanted, and what he wanted to do was understand the nature of matter. Boyle is sometimes called the father of modern chemistry, which is one of those titles that's always a little too neat, a little too clean, but in his case there's a real argument for it. In 1661, he published a book called The Skeptical Chemist, and the title tells you almost everything you need to know about his approach. He was skeptical. He questioned everything. And what he questioned most fiercely was the old idea of elements, both the Aristotelian 4 elements and the alchemical 3 principles of salt, sulfur, and mercury. Boyle's argument was elegant and, when you hear it, kind of obvious. He said, look, if these are truly elements, truly the fundamental building blocks of all matter, then you should be able to break any substance down into them. You should be able to take a piece of wood and decompose it into earth, water, air, and fire, or into salt, sulfur, and mercury. But you can't. When you actually do experiments, when you actually heat things and dissolve things and distill things, you don't get 4 neat elements or 3 neat principles. You get a messy, complicated collection of different substances. So maybe, Boyle suggested, the real elements are something else entirely. Maybe they're substances that can't be broken down any further by any chemical means. That's his definition of an element, and it's essentially the definition we still use today. An element is a substance that cannot be decomposed into simpler substances by chemical reactions. Now, Boyle didn't know what those true elements were, He didn't have a list. He didn't have a periodic table. But he established the criterion, the test, and that was huge. He shifted the question from philosophical speculation to experimental investigation. Don't sit in a chair and theorize about what the elements might be. Go into a laboratory and try to break substances down, and whatever you can't break down further, that's your element. And Boyle did something else that matters enormously. He was rigorous about experimentation. He wrote up his methods in detail so that other people could repeat his experiments and check his results. That sounds basic, almost trivially obvious, but it wasn't standard practice at the time. Alchemists had been deliberately secretive, writing in codes and allegories, hiding their methods. Boyle said no, science has to be open. If your results are real, other people should be able to reproduce them. If they can't, maybe your results aren't as solid as you think. This emphasis on reproducibility, on transparency, on the idea that knowledge should be shared and tested by a community, that's one of the foundations of modern science, and Boyle was one of its strongest early advocates. He also did brilliant work on gases. You might know Boyle's law from school, the one that says, if you compress a gas, its pressure goes up, and if you let it expand, its pressure goes down, in a precise inverse relationship. Pressure times volume equals a constant, as long as the temperature stays the same. Boyle figured this out by doing careful experiments with a J-shaped glass tube and mercury, trapping air in the sealed end and adding mercury to compress it, measuring the volume at each step. It's a beautiful piece of experimental work, patient and precise, and it established one of the first quantitative laws about the behavior of matter. Not just gases can be compressed, which people already knew, but exactly how much they compress for a given increase in pressure. That's the difference between qualitative knowledge and quantitative knowledge, between knowing that something happens and knowing the mathematical relationship that governs it. And that shift from qualitative to quantitative is one of the defining transitions in the history of chemistry. So by the late 17th century, you've got this new framework emerging. Elements defined by experiment rather than philosophy. Gases recognized as distinct substances worth studying. Measurement and reproducibility valued over secrecy and speculation. But there's still a massive piece missing, and it's a piece that's going to dominate chemistry for almost 100 years before it finally gets sorted out. And that piece is combustion. Burning. The most familiar chemical reaction in the world, the one humans have been using since before we were even fully human, and nobody really understands how it works. Here's the problem. When you burn something, like a piece of wood, it seems to lose substance. The wood shrinks, crumbles into ash, and the ash weighs much less than the original wood. So it seems like something is leaving, escaping into the air. That makes intuitive sense. But when you burn a metal, something weird happens. If you heat a piece of iron or tin or lead in air, it forms a crusty residue, what they called a calx, and that calx actually weighs more than the original metal. Something is being added, not lost. So which is it? Does burning involve losing something or gaining something? This contradiction puzzled people for a long time, and in the late 17th century, a German physician and alchemist named Johann Joachim Becher proposed an idea that his student Georg Ernst Stahl would later refine into one of the most influential wrong theories in the history of science. They called the substance phlogiston, from the Greek word for to set on fire, and the theory went something like this. Everything that can burn contains phlogiston. When it burns, it releases its phlogiston into the air. That's what fire is, the visible escape of phlogiston. When wood burns, it loses its phlogiston, and what's left behind is ash, the dephlogisticated wood. Elegant, right? It explains why combustible things stop burning eventually. They run out of phlogiston. It explains why fire needs air, because the air absorbs the phlogiston being released, and once the air is saturated with phlogiston, it can't absorb anymore, and the fire goes out. But what about the metals? What about the fact that a calx weighs more than the original metal? Well, the phlogiston theorists had an answer for that too, though it was a bit strained. Some of them suggested that phlogiston had negative weight, that it actually made things lighter, so when a metal lost its phlogiston, it got heavier. Others just kind of waved their hands at the problem, and for decades, that was good enough. Phlogiston theory worked well enough, explained enough observations, that it became the dominant framework for understanding combustion and chemical reactions throughout most of the 18th century. Some of the best chemists in Europe believed in it completely. And this is where the story gets really interesting, because the person who's going to demolish phlogiston theory, who's going to replace it with something far more powerful and far more true, is already alive by the time phlogiston is at its peak. His name is Antoine Laurent Lavoisier, and he's about to change everything. But before we get to Lavoisier, we need to talk about the people who set the stage for him, the brilliant experimentalists who discovered the gases that Lavoisier would use to build his revolution. Because in the 1760s and 1770s, a remarkable group of chemists, working mostly in Britain, started isolating and identifying gases that no one had ever studied before, gases that had been hiding in plain sight in the atmosphere, in chemical reactions, in the very air we breathe. And the first of them, a quiet, eccentric, almost painfully shy man named Henry Cavendish, was about to discover something extraordinary. Cavendish was the kind of person you'd barely notice at a dinner party, if he even showed up at all. Born in 1731 into one of the wealthiest aristocratic families in England, he had all the money and social connections anyone could want, and he wanted absolutely none of it. He was, by every account, almost pathologically shy. He communicated with his servants by leaving notes. If a woman spoke to him at a gathering, he would literally flee the room. He built a separate entrance to his house so he could come and go without encountering anyone, but put him in a laboratory, and this awkward, reclusive man became one of the most precise and brilliant experimentalists of the 18th century. In 1766, Cavendish published a paper called On Factitious Airs, and it's one of those papers that quietly changes the direction of science. What he'd done was collect and study gases, he called them airs, produced by dissolving metals in acids. Specifically, he dropped zinc, iron, and tin into hydrochloric acid and sulfuric acid, and he carefully captured the gas that bubbled off. This gas was strange. It was incredibly light, far lighter than ordinary air, and it was flammable, wildly, almost explosively flammable. Cavendish called it inflammable air. We call it hydrogen. Now, think about what Cavendish had done. He'd isolated a completely new substance, a gas no one had ever studied in pure form before, and he'd measured its properties with extraordinary care. He figured out its density relative to common air. He noted how it burned. He was meticulous in a way that set a new standard for experimental chemistry. And here's a detail that's easy to overlook but really matters. Cavendish was working within the phlogiston framework. He actually thought inflammable air might be pure phlogiston itself, the very substance that phlogiston theory said was released during combustion. After all, it burned beautifully, which is exactly what you'd expect phlogiston to do. So even though Cavendish's discovery would eventually help destroy phlogiston theory, he himself was a believer. That's one of those ironies that makes the history of science so endlessly fascinating. But Cavendish wasn't the only one making breakthroughs with gases. Around the same time, working in very different circumstances, there was a man named Joseph Black in Edinburgh who had already done pioneering work on what he called fixed air, carbon dioxide, the same gas Van Helmont had noticed a century earlier. Black showed that this gas was produced when you heated limestone, and that it was fundamentally different from ordinary air. He showed it couldn't support combustion or life. He showed it could be absorbed by alkalis, and crucially, he showed that it had weight, that it was a real, measurable substance, not just some vague emanation. Black's careful quantitative approach influenced everyone who came after him. And then there's the man who might be the most fascinating character in this whole story, at least in terms of sheer unlikely biography, Joseph Priestley. If you were going to invent a character for a novel about the discovery of oxygen, you couldn't do better than Priestley. He wasn't a professional chemist. He wasn't trained in natural philosophy. He was a dissenting minister, a Protestant clergyman outside the Church of England, who happened to live next to a brewery in Leeds. And that brewery, with all its fermenting beer producing great clouds of carbon dioxide, got him curious about gases. Priestley was a tinkerer, an improviser, endlessly curious and remarkably inventive in his experimental setups, despite having very little formal training. He figured out how to collect gases over water and over mercury, which let him isolate gases that would have dissolved if collected over water alone. He discovered an astonishing number of new gases, nitrous oxide, which we now use as laughing gas in dentistry, hydrogen chloride, ammonia, sulfur dioxide, silicon tetrafluoride. The man was a gas-discovering machine. But his most important discovery came on August 1st, 1774, and the way it happened is wonderful. Priestley had gotten hold of a large magnifying lens, a burning glass, and he was using it to focus sunlight onto various substances to see what happened when they got extremely hot. On that day, he focused the lens onto a reddish powder called mercuric oxide. Calx of mercury, they called it then. And as the powder heated up, it released a gas. Priestley collected this gas and started testing it. He put a candle in it, and the candle burned with an extraordinary brilliance, far brighter than in ordinary air. He put a glowing splint in it, and it burst into flame. Then he put a mouse in a sealed container of this gas, and the mouse lived far longer than it would have in the same volume of ordinary air. Priestley tried breathing it himself and wrote that his breast felt peculiarly light and easy for some time afterwards. He'd discovered what he called dephlogisticated air, air that had been purified, that had had its phlogiston removed, so it could absorb even more phlogiston during combustion. That's why things burned so brightly in it. We call it oxygen. But here's the thing. Priestley never understood what he'd actually found. He remained committed to phlogiston theory for the rest of his life. He called it dephlogisticated air, and genuinely believed that's what it was. He had the discovery of a lifetime in his hands and interpreted it through a framework that was fundamentally wrong. And that's not a criticism of Priestley. It shows you how powerful a paradigm can be. how even a brilliant experimenter can see the evidence clearly and still fit it into the wrong story. Because the data doesn't speak for itself. It never does. You need the right framework, the right questions, to understand what the data is telling you. And that brings us, finally, to Antoine Laurent Lavoisier. Born in Paris in 1743, into a wealthy family, trained as a lawyer but drawn irresistibly to science. Lavoisier was, in many ways, the opposite of Cavendish. Where Cavendish was reclusive, Lavoisier was sociable, ambitious, well-connected. He married Marie-Anne Pols when she was just 13 and he was 28, and she became not just his wife, but his essential scientific collaborator. She learned English so she could translate the papers of Priestley and Cavendish for him. She studied art so she could create detailed engravings of his experimental apparatus. She took notes during experiments. She hosted the scientific salons where ideas were debated. The Lavoisier were a partnership, and the history of chemistry owes a great deal to both of them. In October 1774, Priestley visited Paris and had dinner with Lavoisier. During that dinner, Priestley told Lavoisier about his new gas, this remarkable dephlogisticated air that made candles burn so brightly and kept mice alive so long. And something clicked in Lavoisier's mind, because Lavoisier had already been thinking hard about combustion, already been troubled by the weight problem that phlogiston theory couldn't cleanly explain. He'd been doing his own careful experiments with burning phosphorus and sulfur in sealed containers, weighing everything before and after with the finest balances available, and he'd noticed that the total weight of the sealed system didn't change. Nothing was being created or destroyed. But the substances that burned gained weight, and the air in the container lost weight by exactly the same amount. Think about what that means. When something burns, it's not releasing some mysterious substance called phlogiston into the air. It's combining with something from the air. It's taking a component of the air into itself. And that component, Lavoisier realized, was Priestley's gas. This was the revolution. Lavoisier repeated Priestley's experiment with mercuric oxide, but he did it with his characteristic precision, weighing everything, measuring the volumes of gas, tracking every gram. He heated the mercuric oxide, collected the gas it released, and showed that this gas was the same component of air that was consumed during combustion. He named it oxygen, from the Greek words meaning acid former, because he believed, incorrectly, as it turned out, that oxygen was a component of all acids. But the name stuck. And then Lavoisier did something even more remarkable. He took Cavendish's inflammable air, hydrogen, and burned it in oxygen. And what formed was water. Pure, ordinary water. Water, which since the time of Thales and Aristotle had been considered a fundamental element, one of the basic building blocks of reality, turned out to be a compound. It was made of two gases combining together, hydrogen and oxygen, joining to form water. You can almost feel the ancient Greek framework crumbling. The four elements, earth, water, air, fire, had been the foundation of thinking about matter for over 2,000 years. And here was Lavoisier showing that water wasn't an element at all, that air was a mixture of different gases, that fire wasn't a substance, but a process, a chemical reaction involving oxygen. Lavoisier published his masterwork in 1789, the same year the French Revolution began. He called it Traité élémentaire de chimie, Elementary Treatise on Chemistry, and it's often considered the first modern chemistry textbook. In it, he laid out a new system. He defined an element the way Boyle had suggested, as a substance that cannot be broken down further by any known chemical means, and he listed 33 of them. Some of his elements were wrong. He included light and heat on the list, which turned out not to be substances at all. But many were right. Oxygen, hydrogen, nitrogen, carbon, sulfur, phosphorus, mercury, iron, gold, silver. These were real elements, and Lavoisier identified them correctly. He also introduced a systematic naming convention for chemical compounds, replacing the old alchemical names, butter of antimony, flowers of zinc, oil of vitriol, with rational names based on composition. Sulfuric acid, carbon dioxide, names that told you what the substance was made of. This was more than just tidying up terminology. It was a new way of thinking. Lavoisier insisted that chemistry had to be quantitative, that you had to weigh and measure everything, that the total mass going into a reaction had to equal the total mass coming out. This is the law of conservation of mass, and while Lavoisier wasn't the first to notice it, he was the first to make it the absolute foundation of chemistry. Nothing is created. Nothing is destroyed. Everything is transformed. That principle, right there, is the bedrock on which all of modern chemistry stands. But Lavoisier's story doesn't end with triumph. The French Revolution, which began the same year his great treatise was published, would consume him, because Lavoisier had another career besides chemistry. He was a tax collector, a member of the Ferme Générale, the private company that collected taxes on behalf of the French crown. It was a lucrative position, and it funded his expensive laboratory and equipment. But it also made him a target. During the Reign of Terror, the revolutionary government arrested the members of the Ferme Générale. Lavoisier was tried, convicted, and on May 8, 1794, he was guillotined. He was 50 years old. The mathematician Joseph Louis Lagrange reportedly said, "It took them only an instant to cut off his head, but France may not produce another such head in a century." Marie-Anne received his belongings after the execution, a small bundle of personal effects sent from the prison. She would spend years afterward working to restore his reputation and publish his remaining papers. She eventually remarried, but she kept the name Lavoisier. So here we are, at the end of the 18th century, and chemistry has been utterly transformed. The phlogiston theory is dead. Oxygen has been discovered. Water has been decomposed. The ancient four elements have been replaced by a growing list of real chemical elements. And the principle of conservation of mass has given chemistry its first truly reliable law. But there's a question that Lavoisier's system couldn't answer, a question that had been lurking in the background since Democritus first proposed his invisible, indivisible particles 22 centuries earlier. What are these elements actually made of? What's happening at the smallest scale? If oxygen and hydrogen combine to form water, what does that actually look like? Are there tiny particles involved? And if so, how do they combine? In what proportions? And why? The person who would tackle that question was a Quaker schoolteacher from the north of England, a man with no university education, no wealthy patrons, no fancy laboratory. His name was John Dalton, and he had been thinking about the weather, of all things, about why the gases in the atmosphere stayed mixed instead of separating into layers, and that seemingly mundane question had led him to something truly radical. Dalton had been keeping meticulous weather journals for years: rain, temperature, barometric pressure, humidity, day after day, filling notebook after notebook in his careful handwriting. And one of the puzzles that nagged at him was this: if the atmosphere is a mixture of different gases, and those gases have different densities, why don't they just separate out? Why doesn't the heaviest gas sink to the bottom and the lightest float to the top, the way oil sits on water? You'd think gravity would sort them, but it doesn't. The atmosphere stays mixed, and Dalton wanted to know why. Now, this might seem like a pretty niche question, but here's where it gets interesting. Dalton reasoned that if each gas in the atmosphere behaves independently, if each gas exerts its own pressure regardless of the other gases present, then maybe that's because the particles of one gas are fundamentally different from the particles of another. Not just different in some vague philosophical sense, but physically different. Different sizes, different weights. And if that's the case, then maybe the reason gases stay mixed is that each type of particle is repelling its own kind, pushing its own particles apart, and those repulsive forces keep everything evenly distributed. Now, his mechanism for why this happened turned out to be wrong. The self-repulsion idea didn't hold up, but the insight underneath it, the idea that each element consists of its own unique type of particle with a specific characteristic weight, that was golden. Dalton presented his atomic theory in stages, starting around 1803 and publishing it more fully in his book, A New System of Chemical Philosophy, which came out in parts beginning in 1808. And the core ideas were beautifully simple. First, all matter is made of atoms, which are indivisible and indestructible. Second, all atoms of a given element are identical in mass and properties. Third, atoms of different elements have different masses. Fourth, chemical reactions involve the rearrangement of atoms. Atoms combine in simple, whole number ratios to form compounds, and they can be separated and recombined, but they're never created or destroyed in a chemical reaction. Think about what that means. If water is always made of hydrogen and oxygen combining in the same fixed ratio by weight, and by Dalton's time, people had measured this, then it makes sense if you imagine that one atom of oxygen always combines with a specific number of hydrogen atoms, not half an atom, not 2/3 of an atom, whole atoms, in definite proportions. It's like a recipe that always calls for exactly 2 eggs and 1 cup of flour. You can't use 1.5 eggs. The ingredients come in discrete units. Now, Dalton wasn't the first person to suggest atoms existed. Democritus had proposed the idea more than 2,000 years earlier, and various natural philosophers had toyed with corpuscular theories of matter in the centuries since. But what Dalton did that was genuinely new was connect the idea of atoms to measurable, quantitative chemistry. He didn't just say atoms exist. He said we can figure out their relative weights. He started building a table of atomic weights, assigning hydrogen a weight of 1, since it seemed to be the lightest, and then calculating the weights of other elements relative to hydrogen based on the proportions in which they combined. Oxygen, he figured, was about 7 times heavier than hydrogen. He was off. The actual ratio is closer to 16:1, and the reason he was off is revealing. He assumed that when 2 elements form only one compound, they combine 1 atom to 1 atom. So he thought water was 1 atom of hydrogen joined to 1 atom of oxygen. In reality, it's 2 hydrogens to 1 oxygen, which is why his oxygen weight came out roughly half what it should have been. But the framework, the method, the idea that you could use chemical analysis to deduce the invisible architecture of matter, that was revolutionary. And here's a lovely detail about Dalton himself. He was colorblind. In fact, he was one of the first people to describe color blindness systematically, and for a long time the condition was actually called Daltonism in several languages. He studied his own vision, realized he couldn't distinguish certain reds and greens, and published a paper about it in 1794. He even requested that after his death, his eyes be preserved and examined to determine the cause. And they were. His eyes were kept in a jar at the Manchester Literary and Philosophical Society for over a century and a half, and in the 1990s, DNA analysis confirmed he had a specific type of color vision deficiency. So here's a man who brought extraordinary precision to understanding the invisible particles of matter, and he couldn't even see colors the way most people do. There's something quietly wonderful about that. But Dalton's atomic weights, imprecise as some of them were, opened a door that other chemists rushed through. One of the most important was a Swedish chemist named Jöns Jakob Berzelius, who was, in many ways, the great systematizer of early 19th century chemistry. Berzelius was meticulous, almost obsessively so. He spent years in his laboratory in Stockholm, performing thousands of careful analyses, determining the composition of compound after compound, and from that work he produced a much more accurate table of atomic weights than Dalton's. By the 1820s, Berzelius had determined the atomic weights of nearly 50 elements with remarkable precision. He's also the person who gave us the chemical notation we still use today, the system where oxygen is O, hydrogen is H, carbon is C, and a molecule of water is written as H2O. Before Berzelius, Dalton had been using little circular symbols, a circle with a dot for hydrogen, a plain circle for oxygen, and so on, which were charming but impractical. Berzelius proposed using the first letter or first two letters of the element's Latin name, and that system stuck. Every chemistry student in the world still uses it. But here's where things get complicated, and honestly, kind of messy in a very human way. There was a serious problem that plagued chemistry for decades in the early 1800s, and it had to do with the difference between atoms and molecules. See, Dalton's theory talked about atoms combining, but it wasn't always clear how many atoms were in a given molecule of a compound, and it wasn't clear whether the basic particles of elemental gases, like hydrogen gas or oxygen gas, were single atoms or pairs of atoms bonded together. And this confusion led to conflicting atomic weights. Different chemists, using different assumptions about molecular formulas, would calculate different atomic weights for the same element. One chemist might say the atomic weight of oxygen was 8. Another might say 16. They were using the same experimental data, but interpreting it differently. An Italian scientist named Amedeo Avogadro had actually proposed a way to resolve this as early as 1811. Avogadro suggested that equal volumes of gases, at the same temperature and pressure, contain the same number of particles. And crucially, he distinguished between atoms and molecules. He proposed that elements like hydrogen and oxygen exist as diatomic molecules, meaning two atoms bonded together, not as single atoms. If you accept that, then the math works out and the atomic weight confusions dissolve. But here's the thing, almost nobody paid attention. Avogadro published his hypothesis, and it was largely ignored for nearly 50 years, partly because he was working in relative isolation in Turin, partly because the distinction between atoms and molecules seemed unnecessarily complicated to many chemists, and partly because the influential Berzelius had his own theoretical framework that didn't accommodate Avogadro's idea easily. So for decades, chemistry was in a state of quiet chaos. The atomic theory was broadly accepted. Most chemists believed in atoms, but there was no consensus on atomic weights, no agreement on molecular formulas, and different textbooks in different countries listed different values for the same elements. Imagine trying to build a science when your fundamental units of measurement are in dispute. It would be like trying to do engineering if nobody could agree on how long a meter was. The person who finally cut through this confusion was an Italian chemist named Stanislao Canizzaro, and the way he did it is one of my favorite stories in the history of chemistry. In 1860, a major international chemistry congress was held in Karlsruhe, Germany, the first truly international chemistry conference ever organized. About 140 chemists from across Europe came together specifically to try to resolve these disputes about atomic weights and molecular formulas. And by most accounts, the conference itself didn't go that well. There were arguments, competing proposals, no clear resolution. But at the very end, as people were leaving, copies of a pamphlet by Cannizzaro were distributed to the attendees. In this pamphlet, Cannizzaro laid out Avogadro's hypothesis clearly and showed, step by step, how it resolved the atomic weight problem. He demonstrated that if you consistently applied Avogadro's principle and recognized that elements like hydrogen, oxygen, and nitrogen exist as diatomic molecules, then all the experimental data fell into place. The atomic weights became consistent, the molecular formulas made sense, and the effect was extraordinary. Not immediately at the conference, but in the months afterward, as chemists went home and actually read the pamphlet. One of those chemists was a young German named Lothar Meyer, who later wrote that reading Cannizzaro's pamphlet was like scales falling from his eyes. Another was a Russian named Dmitry Mendeleev, and both of them, armed with Cannizzaro's corrected atomic weights, would independently notice something remarkable, that when you arrange the elements in order of increasing atomic weight, their chemical properties repeat in a periodic pattern. But that's a story that deserves its own space, and to really appreciate what Mendeleev did, you need to understand the landscape he was working in. The sheer number of elements that had been discovered by the 1860s, the patchwork of knowledge about their behavior, and the various attempts that other chemists had already made to find some kind of order in the growing chaos of the element list. Because by the middle of the 19th century, the number of known elements had exploded. In Lavoisier's time, there were maybe 30-odd substances recognized as elements, and some of those, like light and caloric, turned out not to be elements at all. But in the decades after Lavoisier, new elements were being discovered at a remarkable pace, and a lot of that had to do with a tool that transformed chemistry in ways that are hard to overstate: the electric battery. When Alessandro Volta built the first true battery around 1800, he gave chemists something they'd never had before: a steady, controllable source of electrical current. And it turned out that if you passed electricity through certain chemical compounds, you could break them apart into their constituent elements. This technique, electrolysis, was like a skeleton key for unlocking the composition of matter. Humphrey Davy, working at the Royal Institution in London, used electrolysis to isolate a string of new elements in rapid succession. In 1807 and 1808 alone, he discovered potassium, sodium, calcium, barium, strontium, and magnesium, all by passing electric current through molten compounds that had resisted every previous attempt at decomposition. Potassium was the first, and Davy was reportedly so excited when he saw the tiny globules of a new silvery metal bubbling up from the molten potash that he danced around the laboratory in joy. His cousin Edmund described him as being beside himself with delight. And Davy's story has its own fascinating human dimension. He was charismatic, ambitious, a brilliant lecturer who packed the Royal Institution's auditorium with fashionable London audiences. He came from modest origins in Cornwall, largely self-taught in chemistry, and he rose to become one of the most famous scientists in Britain. He also nearly killed himself multiple times by inhaling various gases in his experiments, including nitrous oxide, laughing gas, which he enthusiastically promoted as producing a pleasurable sensation. He had a complicated relationship with his most famous protege, Michael Faraday, whom he hired as a laboratory assistant and who would eventually surpass him in scientific achievement. Some historians suggest Davy grew jealous of Faraday's rising reputation, and there's evidence he tried to block Faraday's election to the Royal Society. But that's a story that pulls us toward physics and electromagnetism. And right now, what matters is what Davy's discoveries meant for chemistry. Because every new element he pulled from the crucible added another entry to the growing list, another piece of the puzzle, another data point that would eventually need to be organized, categorized, made sense of. Because by the middle of the 19th century, the number of known elements was climbing fast, and it was starting to feel a little overwhelming. Think about it this way. Back in Lavoisier's day, his famous list of elements contained about 33 entries, and some of those were wrong. He included light and caloric, which aren't elements at all. But by the 1860s, chemists knew of roughly 63 elements, and new ones kept turning up. Every few years, someone would isolate another metal from a stubborn mineral, or separate another gas from the atmosphere, and the list would grow by one more. It was like collecting stamps with no album to put them in. You had all these elements: hydrogen, oxygen, carbon, nitrogen, iron, copper, gold, silver, chlorine, bromine, iodine, lithium, sodium, potassium, calcium, barium, aluminum, silicon, phosphorus, sulfur, and they all behaved differently, had different weights, different properties, different affinities. Some were metals, some were gases, some were brittle nonmetals, some reacted violently with water, some didn't react with anything at all. And the question that hung over everything was, is there a pattern here? Is there some underlying order to all of this? Or is nature just handing us elements at random, each one a unique snowflake with no family resemblance to any other? People had tried to find patterns before. Johann Wolfgang Dobereiner, a German chemist, noticed something curious as early as the 1820s. He found that certain elements seemed to come in groups of 3. He called them triads, where the middle element had properties and an atomic weight roughly halfway between the other 2. Chlorine, bromine, and iodine, for example. All 3 were pungent, reactive nonmetals. Bromine's atomic weight sat almost exactly between chlorines and iodines. Same thing with lithium, sodium, and potassium. All soft, reactive metals that went crazy when you dropped them in water. And sodium's weight was close to the average of lithium's and potassium's. Dobereiner found several of these triads, and it was suggestive. It hinted at some deeper relationship, but it didn't go far enough. It was like noticing that some books on your shelf have similar covers without figuring out the organizing principle of the whole library. Others tried too. In 1862, a French geologist named Alexandre-Émile Béguier de Chancourtois arranged the elements by atomic weight on a spiral wrapped around a cylinder. He called it the telluric screw. Elements with similar properties lined up vertically on the cylinder. It was actually a pretty clever idea, and it captured something real about the periodicity of elements. But de Chancourtois published it in a geology journal without the crucial diagram, and almost nobody in the chemistry community noticed. His work was essentially lost to history until people looked back later and said, oh, he was onto something. Then there was John Newlands, an English chemist who in 1865 proposed what he called the law of octaves. He noticed that when you arranged the elements by atomic weight, every eighth element seemed to have similar properties, like notes on a musical scale, where the eighth note is the same as the first, just an octave higher. Hydrogen, lithium, sodium, do, re, mi, and then back to do. It was a genuine insight, and Newlands was brave enough to present it to the Chemical Society of London. But the reception was brutal. One member reportedly asked him whether he'd tried arranging the elements alphabetically, since that might produce equally meaningful results. They laughed at him. The society refused to publish his paper. It was one of those moments in the history of science where someone is essentially right, but slightly too early, slightly too imprecise, and the establishment crushes them for it. Newlands would eventually receive recognition decades later, but at the time, it stung. So the stage was set. Dozens of attempts at classification, none quite convincing enough. And then, in the late 1860s, two men working independently, one in Germany, one in Russia, both cracked the code. Lothar Meyer and Dmitri Mendeleev both created periodic arrangements of the elements that were far more complete and convincing than anything that had come before. And both of them, as we touched on earlier, had been at the Karlsruhe Congress in 1860 and had read Canizzaro's pamphlet, which finally gave them reliable, consistent atomic weights to work with. That's the thing. You can't find the pattern if your data is wrong. All those decades of confusion about atomic weights had been like trying to solve a jigsaw puzzle with pieces from 3 different boxes. Once Cannizzaro sorted out the weights, the picture could finally come together. Lothar Meyer produced a table and a beautiful graph showing how the physical properties of elements, things like atomic volume, rose and fell in a periodic wave when plotted against atomic weight. His work was elegant and convincing. But he didn't publish his most complete table until 1870, and by then, Mendeleev had already beaten him to it. Dmitri Mendeleev. Here's a man worth spending some time with, because his story is wonderful. He was born in 1834 in Tobolsk, Siberia, the youngest of somewhere between 11 and 17 children, depending on which source you trust. His father went blind and lost his teaching position, and his mother ran a glass factory to support the family. When the factory burned down, his mother was determined that Dmitri would get an education, so she traveled with him over 1,000 miles to Moscow, only to be turned away because of enrollment restrictions. She pressed on to St. Petersburg, where he was finally admitted to a pedagogical institute. His mother died shortly after, exhausted from the effort. Mendeleev carried that sacrifice with him for the rest of his life. He dedicated his great work to her memory. He was brilliant, but unruly. Opinionated, with wild hair and a beard he reportedly trimmed only once a year. He was passionate about Russian industry, about education, about vodka standards. He actually helped establish the standard alcohol content for Russian vodka, though the popular story that he set it at exactly 40% is probably embellished. He was a man of enormous energy and strong opinions, and when he turned his attention to the problem of organizing the elements, he attacked it with characteristic intensity. The story goes, and Mendeleev himself told versions of this, that in February 1869, he was working on a textbook, The Principles of Chemistry, and he was struggling with how to present the elements in a logical order. He wrote each element's name, atomic weight, and key properties on a separate card, like a deck of playing cards, and he began arranging and rearranging them. He later said that he saw the pattern in a dream, that he fell asleep exhausted and dreamed of a table where all the elements fell into place. Whether the dream story is literally true or a bit of romantic embellishment, What's certain is that Mendeleev produced his first periodic table in March 1869 and presented it to the Russian Chemical Society. And here's what made Mendeleev's table different from everyone else's attempts. Here's what made it genuinely brilliant. He did two things that no one else had the courage to do. First, he left gaps. Where the pattern demanded an element that nobody had yet discovered, Mendeleev simply left a blank space and said, "This element exists, we just haven't found it yet." Second, in a few cases, where an element's accepted atomic weight would put it in the wrong place in the pattern, he boldly said the atomic weight must be wrong and rearranged accordingly. He trusted the pattern more than the data. That takes extraordinary confidence. And then he went further. For 3 of those gaps, he made detailed predictions about the missing elements, their atomic weights, their densities, their melting points, the types of compounds they would form, even what their oxides would look like. He called them eka-boron, eka-aluminum, and eka-silicon, using the Sanskrit prefix eka, meaning one beyond. He was essentially saying, here is an element that should exist right below aluminum in my table, and when you find it, here's exactly what it will be like. And then they found them. Gallium was discovered by the French chemist Paul-Émile Lecoq de Boisbaudran in 1875, and its properties matched Mendeleev's predictions for eka-aluminum almost perfectly. When Lecoq initially reported a density that differed slightly from Mendeleev's prediction, Mendeleev had the audacity to write to him and suggest he remeasure. And when Lecoq did, the new measurement matched Mendeleev's prediction, not the original measurement. Think about that for a second. A man predicts the properties of an element that hasn't been discovered yet, and when the discoverer's measurements don't match the prediction turns out to be right, and the measurement wrong. That's an extraordinary moment in the history of science. Scandium followed in 1879, matching eka-boron. Germanium came in 1886, matching eka-silicon with stunning precision. Its atomic weight, density, specific heat, the formula and boiling point of its chloride compound, all almost exactly as Mendeleev had predicted 17 years earlier. By this point, the chemistry world was convinced. The periodic table wasn't just a convenient arrangement. It was revealing something deep and true about the structure of matter. There was a law here, a periodicity, a repeating rhythm in the properties of elements when ordered by atomic weight. Now, Mendeleev didn't know why the pattern existed. He couldn't explain the underlying cause of periodicity. That would require understanding atomic structure, electrons, quantum mechanics, concepts that were decades away. He just saw the pattern and trusted it. And that's often how science works. You see the regularity before you understand the mechanism. Kepler saw that planets move in ellipses before Newton explained why. Mendeleev saw that element properties repeat periodically before anyone knew about electron shells. But even as the periodic table was transforming how chemists thought about elements, another revolution was quietly underway. One that would reshape not just chemistry, but the entire economy of the industrialized world. Because around the same time, Mendeleev was arranging his cards on a table in St. Petersburg. Chemists in Germany and Britain were figuring out how to do something that would have seemed like sorcery to earlier generations. They were learning to build molecules from scratch, not just analyzing what nature provided, not just breaking things apart, but actually constructing new substances that had never existed before on Earth. And the first great triumph of this synthetic chemistry came from an unlikely place, a teenager's failed experiment, and a substance so vivid and so commercially valuable that it would launch an entire industrial revolution in molecule building. His name was William Henry Perkin, and in 1856, he was 18 years old, working in a makeshift laboratory he'd set up in his family's apartment in the East End of London. His teacher at the Royal College of Chemistry was August Wilhelm von Hofmann, a German chemist who'd been recruited to London and who had a particular fascination with coal tar. That thick, foul-smelling black sludge left over when you heated coal to make gas for city street lamps. Coal tar was basically industrial waste. Cities were producing mountains of the stuff, and nobody quite knew what to do with it. But Hofmann had been picking apart coal tar's chemical components and finding all sorts of interesting organic compounds hiding inside: benzene, toluene, aniline, naphthalene. He suspected these could be useful building blocks for making other things. Now, Hofmann had floated an ambitious idea to his students. What if you could synthesize quinine from coal tar chemicals? Quinine was the only effective treatment for malaria, and it came exclusively from the bark of the cinchona tree, which grew in South America, the British Empire, sprawling across tropical regions where malaria killed soldiers and colonists by the thousands, desperately needed a cheaper, more reliable source. If you could make quinine in a lab from cheap coal tar waste, you'd have a product worth a fortune. So, young Perkin, during his Easter break, decided to give it a try. He took aniline, one of those coal tar derivatives, and tried to oxidize it with potassium dichromate, hoping through a series of reactions to build up the complex quinine molecule. Now here's the thing. Perkin had essentially no chance of succeeding. The structure of quinine is enormously complicated, with multiple rings and specific arrangements of atoms that nobody in 1856 had the tools or knowledge to construct deliberately. Organic chemistry was still in its infancy. Chemists barely understood molecular structure. Kekulé wouldn't even propose the ring structure of benzene for another 9 years. Perkin was, in a sense, trying to build a Swiss watch with a hammer, and predictably, he didn't get quinine. What he got was a reddish-brown sludge at the bottom of his flask. A mess. A failure. Most people would have washed it out and moved on. But Perkin noticed something. When he added alcohol to try to clean the flask, the sludge dissolved into a vivid, striking purple solution. A beautiful, rich, luminous purple. And something about that color caught his attention. He dipped a piece of silk into it, and the silk turned purple. A gorgeous, lasting purple that didn't wash out easily and didn't fade quickly in sunlight. Now, you have to understand what purple meant in the 1850s. Purple dye had been one of the most expensive substances in the world for millennia. The ancient Tyrian purple came from sea snails. Thousands of snails crushed to produce a tiny amount of dye. Purple was literally the color of royalty, because almost nobody else could afford it. Even by the mid-19th century, purple and mauve fabrics were expensive, the dyes unreliable, and the colors often dull. And here was an 18-year-old with a flask full of vibrant purple made from coal tar. From garbage, essentially. Perkin had the entrepreneurial instinct to recognize what he had. He tested the dye's fastness, how well it held up to washing and light. He sent samples to a dyeing firm in Scotland. The response was enthusiastic. Within a year, Perkin had patented his dye, which he called aniline purple, and which the French would christen mauvaine. He dropped out of the Royal College of Chemistry. Hofmann was not pleased, and with financial help from his father, built a factory in Greenford, west of London, to manufacture the dye commercially. He was 19 years old. The timing was perfect. Queen Victoria wore a mauvain-dyed dress to her daughter's wedding in 1858. Empress Eugénie of France loved the color. Suddenly mauve was everywhere. Fashion magazines, ball gowns, postage stamps. The craze was so intense that the late 1850s were sometimes called the Mauve Decade. And Perkin got rich. But here's what's really important about this story. It's not just about one dye and one lucky teenager. Perkin's Mauvain proved a concept. It demonstrated that you could take cheap, abundant waste chemicals and transform them into valuable products through deliberate chemical reactions. That idea, that chemistry could be a manufacturing enterprise, that molecules could be designed and built for commercial purposes, that idea changed the world. And it was the Germans who ran with it furthest. Hofmann eventually returned to Germany, and German universities and German industry formed an extraordinarily productive partnership. German chemists systematically attacked the problem of synthetic dyes, not through lucky accidents, but through methodical research. They figured out the structures of natural dyes, then figured out how to synthesize them more cheaply. Alizarin, the red dye from madder root that had been used since ancient Egypt, was synthesized independently by Karl Graebe and Karl Liebermann in 1868, and then scaled up industrially by the German firm BASF. Within a decade, the natural madder industry, which had employed tens of thousands of farmers in France and elsewhere, was essentially destroyed. Synthetic alizarin was cheaper, more consistent, and available in unlimited quantities. Then came the big one: indigo, the deep blue dye that colored blue jeans and naval uniforms and had been extracted from plants for thousands of years. Adolf von Baeyer spent nearly 2 decades working out the structure and synthesis of indigo, finally achieving it in the 1880s. BASF then invested a staggering amount of money, some estimates say the equivalent of $1 billion in today's terms, into developing an industrial process to manufacture synthetic indigo cheaply enough to compete with the natural product. They succeeded around 1897, and within a few years, the indigo plantations of India, which had been a cornerstone of the colonial economy, collapsed. Think about what that means. Chemistry wasn't just an academic pursuit anymore. It was an economic weapon. It could create entire industries overnight and destroy others that had existed for centuries. The great German chemical companies, BASF, Bayer, Hoechst, Agfa, became some of the largest and most powerful corporations in the world, and they did it by hiring PhD chemists by the hundreds and investing heavily in research laboratories. This was arguably the birth of industrial research and development as we know it. And the thing about synthetic dyes is that they were just the beginning. Once you have chemists who understand how to manipulate organic molecules, how to attach this group here, remove that atom there, build rings and chains and bridges, once you have that capability, dyes are just one application. The resistance of certain dyes to biological processes led to a stunning insight. If a dye molecule could selectively stain certain types of cells or bacteria, maybe a modified version of that molecule could selectively kill bacteria without harming human cells. This was the thinking that led Paul Ehrlich, working in the 1890s and early 1900s, to develop the concept of a magic bullet, a chemical compound designed to target a specific disease organism. Ehrlich systematically tested hundreds of synthetic compounds against the syphilis bacterium, and in 1910, compound number 606, arsphenamine, marketed as salvarsan, proved effective. It was the first modern chemotherapeutic agent, the first drug deliberately designed through chemical reasoning to treat a specific disease. So you can draw a direct line from Perkins' dirty flask in 1856 to the birth of the pharmaceutical industry. Dyes led to drugs. Coal tar chemistry led to medicine. And this is a pattern you see again and again in the history of chemistry. Discoveries in one area cascade into completely unexpected fields. But let's step back for a moment and talk about what was happening on the more fundamental side of chemistry during this same period. Because the late 19th century was also when chemists started grappling seriously with a question that had been lurking since Dalton. What exactly is a chemical bond? What holds atoms together in a molecule? Dalton had drawn his atoms as little circles with hooks, almost literally imagining them latching onto each other mechanically. But that was obviously just a placeholder. The real question: why do 2 hydrogen atoms and 1 oxygen atom combine to form water? Why not 3 hydrogens? Why not 1? That question pointed towards something deeper about the nature of atoms themselves. The concept of valence emerged gradually through the 1850s and 1860s. Edward Franklin noticed that certain metals seemed to combine with a fixed number of other atoms. He called it their combining power. Kekule, that same chemist who proposed the benzene ring, argued that carbon always forms 4 bonds, and he used this insight to start explaining the structures of organic molecules. Carbon's four-handedness, its tetravalence, turned out to be the key to understanding why organic chemistry is so extraordinarily rich and varied. With 4 bonds, a carbon atom can link to other carbons in chains, branches, rings, and 3-dimensional frameworks, creating an almost infinite variety of molecular architectures. And then in 1874, 2 young chemists working independently, Jacobus Henricus van 't Hoff in the Netherlands and Joseph Achille Lebel in France, proposed something remarkable. They suggested that carbon's 4 bonds aren't flat, aren't arranged in a plane, but point outward toward the corners of a tetrahedron. A 3-dimensional arrangement. This meant that molecules had shape, real physical 3-dimensional shape, and that the same atoms connected in the same order could sometimes be arranged in 2 mirror image forms, like left and right hands. This was the birth of stereochemistry, the understanding that the spatial arrangement of atoms matters enormously. It explained puzzling observations, like why certain compounds rotated polarized light in different directions, and it would eventually turn out to be absolutely crucial in biology and medicine, because enzymes and receptors in your body are exquisitely sensitive to molecular shape. The wrong mirror image of a drug molecule might be useless, or worse, harmful. So by the last quarter of the 19th century, chemistry had transformed almost beyond recognition from what it had been just 100 years earlier, when Lavoisier was carefully weighing his flasks. Chemists now had a periodic table that organized the elements and predicted new ones. They had structural formulas that showed how atoms were arranged in molecules in 3 dimensions. They had a booming synthetic chemical industry that was producing dyes, drugs, explosives, and perfumes. They understood stoichiometry, thermodynamics was being applied to chemical reactions, and the concept of chemical equilibrium was being formalized. But there was still a gaping hole at the center of it all. Atoms were clearly real. Almost everyone accepted that by now. But nobody knew what an atom actually was. Was it truly indivisible, as Dalton had assumed, as the very word atom implied? Or did it have internal structure? And if it had structure, what was inside? The answer to that question was about to arrive, and it would come not from chemistry, but from physics. from a series of experiments involving glass tubes, electrical discharges, and a strange greenish glow that appeared when you pumped most of the air out of a sealed glass tube and ran a high voltage through it. Physicists had been playing with these tubes since the middle of the century. Heinrich Geissler made beautiful ones in the 1850s, and William Crookes refined them further in the 1870s. And they noticed that something was streaming from the negative electrode, the cathode, across the vacuum to the other end, making the glass itself fluoresce with that eerie glow. They called them cathode rays, which was really just a name for something nobody understood yet. Were they waves? Were they particles? Nobody was sure. And then, in 1897, J.J. Thomson at the Cavendish Laboratory in Cambridge did something beautifully simple. He put electric and magnetic fields around the beam and measured how much the rays deflected. From the deflection, he could calculate the ratio of the charge to the mass of whatever was carrying the beam. And here's what stunned everyone. The mass was tiny, absurdly tiny, about 1/1800th the mass of a hydrogen atom, the lightest atom known. Thomson had found a particle smaller than an atom. He called them corpuscles at first, though the name electron, coined earlier by the Irish physicist George Johnstone Stoney, is what stuck. And just like that, the atom was no longer indivisible. It had parts. Something was inside it. Now, think about what that meant for chemistry. For a century, chemists had been building an entire science on the idea that atoms were the fundamental building blocks, the smallest things that mattered. And they were right to do that. It worked brilliantly for stoichiometry, for the periodic table, for structural formulas. But now there was a deeper layer, and it turned out that this deeper layer was exactly what was needed to explain the thing chemists had always struggled with most. Why do atoms bond to each other in the first place? Why does sodium always combine with chlorine in a 1-to-1 ratio? Why does carbon form 4 bonds and oxygen 2? Valence had been a useful rule, but it was just a pattern. Nobody knew the mechanism. The electron was going to provide the mechanism. But first, people had to figure out how the atom was actually put together. Thomson proposed his plum pudding model. Imagine a sort of blob of positive charge with electrons embedded in it, like raisins in a pudding. It was a reasonable guess given what was known. But it didn't last long. In 1909, Ernest Rutherford, a New Zealander working in Manchester, directed his students Hans Geiger and Ernest Marsden to fire alpha particles, which are basically helium nuclei, little positively charged bullets, at a thin gold foil. Most of the alpha particles sailed right through, which was expected, but a few bounced back at sharp angles. Some came almost straight back toward the source. Rutherford later said it was as if you'd fired an artillery shell at tissue paper and it came back and hit you. That result was completely incompatible with the plum pudding. It meant the positive charge and almost all the mass of the atom were concentrated in a tiny, dense core, the nucleus, with the electrons orbiting far away in mostly empty space. The atom, it turned out, was almost entirely nothing. If you blew up an atom to the size of a football stadium, the nucleus would be about the size of a marble on the 50-yard line, and the electrons would be gnats buzzing around the upper decks. This was exhilarating and terrifying for chemistry at the same time, because it immediately raised a problem. Classical physics said that an electron orbiting a nucleus should continuously radiate energy, the way any accelerating charged particle does, and spiral inward, crashing into the nucleus in a fraction of a second. But atoms obviously don't collapse. They're stable. Something was wrong with the classical picture. The resolution came from a young Danish physicist named Niels Bohr. who in 1913 proposed something radical. He said electrons could only occupy certain specific orbits around the nucleus, each with a fixed energy. They couldn't spiral inward continuously because they couldn't exist between those allowed orbits. They could jump from one orbit to another, absorbing or emitting a precise amount of energy in the process, but they couldn't gradually decay. This was one of the earliest applications of quantum theory to atomic structure, building on Max Planck's idea from 1900 that energy comes in discrete packets, quanta, rather than flowing continuously. Bohr's model was crude. It worked well for hydrogen, but struggled with anything more complex. And within a decade, it would be superseded by the full quantum mechanical treatment developed by Schrödinger, Heisenberg, Dirac, and others in the mid-1920s. But even in its simple form, Bohr's model gave chemistry something priceless, a physical explanation for the periodic table. Here's how. If electrons occupy specific energy levels, or shells, and each shell can hold only a certain number of electrons, then the chemical behavior of an element depends on how many electrons are in its outermost shell. Hydrogen has 1 electron, helium has 2, and 2 fills the first shell completely, which is why helium is inert. It has no need to gain or lose electrons. Lithium has 3 electrons, so 2 fill the first shell, and 1 starts a new outer shell, making lithium chemically reactive in a way that's similar to hydrogen and sodium, which also have 1 electron in their outermost shell. And there it was, the explanation for Mendeleev's columns. Elements in the same column of the periodic table have the same number of outer electrons. That's why they behave similarly. The periodic table wasn't just a clever organizational scheme. It was a map of electron configurations. This is one of those moments in the history of science that gives you chills if you sit with it. Mendeleev arranged his elements by atomic weight and chemical behavior in 1869, decades before anyone knew electrons existed, decades before quantum mechanics. And yet the pattern he found was real, and it was ultimately explained by the quantum structure of the atom. He was reading the consequences of quantum mechanics in the laboratory behavior of elements without having any idea what was causing it. It's like someone in the 18th century mapping ocean currents perfectly without knowing the Earth rotates. Now, the full quantum mechanical picture that emerged in the 1920s replaced Bohr's neat circular orbits with something stranger and more beautiful: orbitals. An orbital isn't a path the electron follows, like a planet going around the sun. It's a probability cloud, a mathematical function that tells you where the electron is likely to be found. Some orbitals are spherical, some are dumbbell-shaped, some look like 4-leaf clovers, and the way these orbitals overlap and combine when atoms come together, that's what a chemical bond actually is. When 2 hydrogen atoms approach each other, their electron orbitals merge into a new, shared orbital that wraps around both nuclei, and the electrons spend most of their time in the space between the 2 nuclei, holding them together. That's a covalent bond, described at the quantum level. Linus Pauling, an American chemist working at Caltech, did more than perhaps anyone else to translate quantum mechanics into the language of chemistry. His 1931 paper on the nature of the chemical bond and his landmark 1939 book of the same name showed chemists how to use quantum ideas, hybridization, resonance, electronegativity, to understand molecular structure and reactivity. Pauling won the Nobel Prize in Chemistry for this work in 1954, and he remains one of only 2 people ever to win 2 unshared Nobel Prizes, the other being for peace in 1962. So by the 1930s and 1940s, the ancient question, what holds matter together, finally had a real answer, rooted in physics but expressed in chemistry. And this understanding didn't just sit in textbooks. It changed what chemists could do. If you understand why bonds form and break, you can design reactions more intelligently. You can predict which molecules will be stable and which won't. You can start to engineer molecules for specific purposes. And this is exactly what happened in the middle of the 20th century, on a scale that would have been unimaginable to Lavoisier or even Mendeleev. The polymer revolution is a perfect example. People had been working with natural polymers forever: rubber, cellulose, silk, wool. But the idea that these materials were made of enormously long chain molecules was controversial well into the 1920s. Hermann Staudinger, a German chemist, championed the concept of macromolecules against fierce opposition from colleagues who insisted that materials like rubber were just loose aggregates of small molecules. Staudinger was stubborn and right, and he eventually won the Nobel Prize in 1953 for proving that polymers were genuine giant molecules with covalent bonds running the entire length of the chain. Once that was established, the floodgates opened. Wallace Carruthers at DuPont synthesized nylon in the mid-1930s, the first fully synthetic fiber, created by understanding how small molecules could be linked into long chains through condensation reactions. Nylon stockings went on sale in 1940, and 4 million pairs sold on the first day. Then came polyethylene, polystyrene, PVC, Teflon, polyester, polycarbonate, an avalanche of synthetic materials that reshaped daily life in ways so thorough that you probably can't look around any room you're in without seeing a dozen things made from them. Your phone case, the insulation on every wire in your walls, the fabric of half your clothes, the lenses in modern eyeglasses, the dashboard of your car. All of it descended from the understanding that carbon atoms can link into long chains, and that the properties of the resulting material depend on the chain's length, its branching, and what other atoms are hanging off it. And polymers were just one thread. The same decades saw the rise of modern pharmaceutical chemistry, where understanding molecular shape and electronic structure allowed chemists to design drugs with increasing precision. Remember Ehrlich's magic bullet idea from the early 1900s? By mid-century, that dream was becoming real. The discovery of penicillin. Alexander Fleming noticed the mold killing bacteria in 1928, and Howard Florey and Ernst Boris Chain figured out how to purify and mass-produce it during World War II. That was partly serendipity. But the resistance to penicillin that soon appeared drove chemists to understand exactly how the molecule worked, how bacteria broke it down, and how to modify its structure to stay one step ahead. That's medicinal chemistry in action. Tweaking a molecule's shape, adding a group here, removing one there, testing how each change affects its interaction with a biological target. It's three-dimensional chess played with atoms, and it depends entirely on the understanding of bonding and molecular geometry that Pauling and others had built. Meanwhile, another revolution was quietly brewing, one that would connect chemistry to biology in the most profound way imaginable. By the late 1940s, scientists knew that genes were made of DNA, deoxyribonucleic acid, a molecule that had been isolated way back in 1869 by Friedrich Miescher, but largely ignored for decades because everyone assumed proteins, with their 20 different amino acid building blocks, must carry genetic information. DNA seemed too simple, with only 4 nucleotide bases. But Oswald Avery's experiments in 1944 strongly suggested DNA was the genetic material, and by the early 1950s the race was on to determine its structure. And this is where chemistry, physics, and biology converged in one of the most famous stories in all of science. The story of a photograph, a helix, and a molecule that changed everything. Rosalind Franklin was the one who took that photograph. And it's worth pausing here, because her story matters, not just for what she contributed, but for what it tells us about how science actually works, who gets credit, and how chemistry at its highest level is as much about careful, painstaking technique as it is about flashes of brilliance. Franklin was a physical chemist trained at Cambridge, and by the early 1950s she was working at King's College London, using X-ray crystallography to study the structure of DNA. X-ray crystallography. You might remember, this is the technique where you fire X-rays at a crystal or a fiber, and the way the rays scatter tells you about the arrangement of atoms inside. It's pure chemistry and physics working together. You need to prepare the sample perfectly. You need to align the X-ray beam just right. You need to expose the film for exactly the right amount of time. And then you need the mathematical skill to interpret the pattern of spots and streaks on the resulting photograph. Franklin was exceptionally good at all of this. In May 1952, she and her graduate student, Raymond Gosling, produced an X-ray diffraction image of DNA in its wet or B form. It's known as photograph 51, and when you hear scientists talk about it, there's a kind of reverence in their voices, because this single image contained the key to one of the biggest questions in the history of science. The pattern on the photograph, a distinctive X-shaped arrangement of dark spots, was the signature of a helix. Franklin knew this. She was methodically working through the mathematics, calculating the dimensions, the spacing between the turns, the number of chains. She was cautious, rigorous, the kind of scientist who doesn't announce results until she's certain. But here's where the story gets complicated and, honestly, a little painful. Without Franklin's knowledge or permission, her colleague Maurice Wilkins showed photograph 51 to James Watson, a young American biologist working with Francis Crick at Cambridge. Watson and Crick were trying to build a physical model of DNA, literally constructing it from metal plates and rods like a three-dimensional jigsaw puzzle. They'd already tried once and gotten it wrong, proposing a triple helix with the bases facing outward. When Watson saw Franklin's photograph, he immediately recognized the helical signature, and the specific pattern told him the helix had to have 2 chains, not 3. Combined with Erwin Chargaff's earlier finding that the 4 DNA bases always appeared in specific ratios, adenine matching thymine, guanine matching cytosine, Watson and Crick were able to build their famous double helix model. They published it in April 1953 in Nature, a paper of barely more than a page, one of the most consequential pages in the history of science. And what makes this a chemistry story, not just a biology story, is that the double helix is fundamentally a chemical structure. The 2 strands are held together by hydrogen bonds between the base pairs, those weak but numerous interactions that Pauling had described so beautifully. The backbone of each strand is a chain of sugar and phosphate groups connected by covalent bonds. The specific pairing, A with T, G with C, works because of molecular shape and hydrogen bonding geometry. Adenine and thymine fit together perfectly, forming 2 hydrogen bonds. Guanine and cytosine fit together, forming 3. It's like a lock and key, but the lock and key are made of atoms, and the fit is determined by bond angles and electron distributions. Everything Pauling had taught chemists about the nature of the chemical bond was right there, holding the secret of life together. Franklin died of ovarian cancer in 1958, at the age of 37, likely caused by her extensive exposure to X-rays during her research. Watson, Crick, and Wilkins received the Nobel Prize in 1962. The Nobel is not awarded posthumously, so Franklin was not eligible, but the historical record is clear about the centrality of her contribution. It's one of those stories that reminds you that science is done by real people, with all the messiness that implies. Now the discovery of DNA's structure opened up an entirely new chapter in chemistry, one we're still writing. Because once you know the structure, you can start to understand the mechanism. How does DNA copy itself? The double helix practically tells you. The two strands separate, and each one serves as a template for building a new complementary strand. How does genetic information get turned into proteins? That involves RNA, ribosomes, transfer molecules, an intricate molecular machinery that chemists and biologists spent the next several decades working out. The genetic code itself, the correspondence between three-letter sequences of DNA bases and specific amino acids, was cracked by the mid-1960s. And all of it, every bit of it, is chemistry. It's molecules interacting with molecules, bonds forming and breaking, shapes fitting together or not. This convergence of chemistry and biology accelerated through the second half of the 20th century in ways that would have been unimaginable to Lavoisier or even Pauling. By the 1970s, chemists and biologists had developed tools to cut DNA at specific sequences using restriction enzymes, to splice pieces together, to insert genes from one organism into another. Recombinant DNA technology it was called, and it was essentially molecular engineering, using the tools of chemistry to edit the instructions of life. The first genetically engineered product to reach the market was human insulin, produced by bacteria that had been given the human insulin gene, approved in 1982. Think about that. For decades, diabetics had relied on insulin extracted from pig or cow pancreases. Now, bacteria in a fermentation vat were reading human DNA and producing human insulin, identical to what your own body makes. That's chemistry and biology fused so completely you can't tell where one ends and the other begins. And this brings us gently to where chemistry stands today, or rather, where it flows, because it's not standing still. It never has been. The boundaries that once separated chemistry from physics and biology have become so blurred, they're almost meaningless. A modern chemist might spend their morning running quantum mechanical calculations on a supercomputer, predicting how a new molecule will behave before it's ever been synthesized. They might spend their afternoon in a lab using techniques that would make Lavoisier weep with envy. Nuclear magnetic resonance spectroscopy to determine molecular structure, mass spectrometry to identify unknown compounds with extraordinary precision, electron microscopy to actually see individual molecules. And they might spend their evening reading a paper about CRISPR, the gene editing tool derived from a bacterial immune system, which is essentially a chemical machine for making precise cuts in DNA. Here's what's really remarkable when you step back and look at the whole arc of this story. Chemistry began with people noticing that stuff changes. Fire turns wood to ash. Grapes become wine. Certain rocks, when heated with charcoal, yield shiny metal. For thousands of years, that's all it was. Observation and craft, trial and error, recipes passed down and slowly improved. The Greek philosophers tried to reason about what matter was made of, but they didn't do experiments. So their ideas, brilliant as some of them were, remained speculation. The alchemists added systematic laboratory technique and a passion for transformation, but they were chasing impossible goals with an inadequate theoretical framework. It took the scientific revolution, Boyle insisting on experimental evidence, Lavoisier insisting on careful measurement, Dalton proposing atoms with specific weights, to turn chemistry into a science. And then the 19th century built the grand architecture, the periodic table organizing the elements, structural theory explaining how atoms connect, thermodynamics explaining why reactions happen. And the 20th century? The 20th century revealed the quantum mechanical foundations underneath all of it. Why the periodic table has the shape it does, why carbon forms four bonds, why some molecules are mirror images of each other, why certain reactions release energy and others require it. The answers were always there, written in the behavior of electrons, but it took the combined genius of physicists and chemists, Thomson, Rutherford, Bohr, Schrödinger, Pauling, and so many others, to read that writing. You know what I find most beautiful about this whole story? It's that chemistry is the science of the in-between. Physics deals with the fundamental particles and forces. Biology deals with living systems. Chemistry occupies the space between. It's the science of how atoms come together to make molecules and how molecules interact to create the material world. Every object you can touch, every breath you take, every sensation you feel, it's all chemistry. The hemoglobin in your blood carrying oxygen is a chemical marvel, an iron atom cradled in a porphyrin ring, its electronic structure shifting subtly as it binds and releases oxygen molecules. The screen you looked at today, if you looked at one, relies on liquid crystals or organic light-emitting diodes, molecules designed by chemists to interact with light in precise ways. The coffee or tea you might have had this morning, the flavors and aromas, those are volatile organic compounds interacting with receptor proteins in your nose and tongue. Chemistry everywhere, all the time, usually invisible, always essential. And the story isn't over, not even close. Chemists today are working on challenges that would define the next century. Energy storage, better batteries, new materials for solar cells, catalysts that can split water into hydrogen and oxygen using sunlight, the way plants have been doing for billions of years through photosynthesis. Carbon capture, finding ways to pull carbon dioxide out of the atmosphere and convert it into something useful, essentially running combustion in reverse. New medicines, not just small molecules anymore, but antibodies, gene therapies, mRNA vaccines like the ones developed with breathtaking speed during the COVID-19 pandemic, which are fundamentally chemical technologies, molecules designed to instruct your own cells to produce a specific protein. Materials science, self-healing polymers, biodegradable plastics, superconductors, metamaterials with properties that don't exist in nature. Every one of these challenges requires the same thing chemistry has always required: understanding how atoms and molecules behave, and using that understanding to make something new. The tools are unimaginably more powerful than anything Lavoisier or Dalton or even Pauling had. But the fundamental question is the same one that the first human asked when they watched wood burn in a fire. What just happened? What is this stuff made of? And can I make it do something useful? So as you lie there, maybe drifting a little, maybe already halfway to sleep, think about this. You are, right now, a walking chemistry experiment. Your body is running thousands of chemical reactions every second. Enzymes catalyzing reactions, ions flowing across membranes to carry nerve signals, ATP molecules being built and broken down to power your muscles and your thoughts. The oxygen you're breathing in is binding to hemoglobin, and the carbon dioxide you're breathing out is the waste product of cellular respiration, the same combustion reaction Lavoisier identified in the 1770s, just controlled and gentle and happening at body temperature instead of in a flame. You are made of atoms forged in stars, carbon, nitrogen, oxygen, iron, all cooked up in stellar furnaces billions of years ago and scattered across the cosmos when those stars exploded. Chemistry connects you to the universe in the most literal way possible. And that's the story. From campfires to quantum mechanics, from alchemists searching for gold to chemists designing molecules that can edit genes. It's a story of curiosity, of people who looked at the world and refused to accept that it was unknowable. They asked questions, they built instruments, they made mistakes, they argued with each other, and piece by piece, Century by century, they figured out what matter is and how it works. Not all of it, not yet, but enough to transform the world beyond recognition, enough to save millions of lives with medicines and clean water, enough to build materials that nature never imagined, enough to begin understanding the molecular machinery of life itself. It's a good story, and it's still being written by people in labs all over the world right now, tonight, while you rest. So let that thought carry you off, the quiet knowledge that somewhere, someone is mixing two things together and watching what happens, the same way humans have been doing for thousands of years. And maybe tomorrow, they'll discover something no one has ever seen before. But for now, that can wait. Everything can wait. Just breathe and let the chemistry of sleep do its gentle, ancient work.